Yeah, why did you know? You're the documentary lover.
Okay, you guys, so
I knew you're that one.
yesterday we left off with this picture here. And this picture was illustrating the second part of cell signaling. So remember, the first part is the reception, the signal molecule binds. The second part is transduction, that was this. And then the third part is the response, which is what we get after this. And so remember that this transduction pathway is a series of proteins that become activated. How do they become activated, Roman? Phosphorylation, that's right. So adding a phosphate group. And so, this phosphate, these molecules that are inactive become active by adding phosphate groups. And these kinases are enzymes that's what they do. They add phosphate groups to make molecules become active. And so then this molecule is active and it phosphorylates the next molecule, and that phosphorylates the next molecule until eventually you get the molecule phosphorylated as your active protein, and that's what gives you your cellular response. And then remember, those phosphate groups are taken off at the end so that you can stop that cellular response. And so that's what those phosphatase enzymes do, is take off the phosphate groups and deactivate it. So therefore, to get a continual cellular response, you need a continual supply of signal molecules, all right, so that this response can happen. Because the signal molecule doesn't stay on forever. So when it binds, it triggers this pathway to elicit a response, and then it detaches. So to keep doing this response, all these guys are going to be deactivated by taking the phosphates off, so then you have to have another signal molecule, and so on and so forth. So if this signal molecule is a hormone, then your body has to continually supply that hormone so that it can continually bind to the membrane and elicit a cellular response. All right, so now what we're going to do is look at a couple of different examples of this. And so I'm going to introduce you to something called a second messenger. So second messengers are small, non-protein, water-soluble molecules, or ions. The extracellular signal molecule that binds to the membrane is the first messenger, and then can trigger what's called a second messenger that can readily spread through the cell by diffusion. Second messengers participate in pathways initiated by G protein-linked receptors and receptor kinases. And the G protein-linked receptors and receptor kinases, what those are two examples of how a receptor works. So these two, remember yesterday we talked about different kinds of receptors. There's receptors in the membrane, and then there are receptors that are part of the membrane. And so the G protein-linked receptors and the tyrosine kinases receptor systems are examples of this one right here. So I'm going to go through specific examples using this and relating it to this transduction pathway. So before I do that, I'm going to show you just a little animation from the website that correlates with our textbook, so you can visually see what's going on, which will help you to visualize what I'm going to talk about in just a second here with examples of this. And so I'm going to pull up the website. Remember a while ago I gave you the instruction sheet to sign into that. If you haven't done so, it can be helpful for you. When you sign in and register, this is what it looks like. You click here, study area in the corner here. It comes up, pops up, and it looks like this. There's a drop-down menu. We're in chapter 11, so I'm going to go to chapter 11 and hit go. And so then this is the chapter guide. And I'm going to go down here. Reception is in the second section. And so notice it says here there's an activity that is called reception, so I'm going to click on that.
Most signal molecules act on target cells by binding to receptors in the cell membrane. There are several kinds of membrane receptors. Some signal molecules enter target cells and bind to intracellular receptors in the cytoplasm. 4 different kinds of receptors are shown here. Click on each receptor to study its function.
So I'm going to click on the G protein linked receptor because I'm going to go through some examples of that so you can just see how things move around and how this reception works. So here we go.
Many signal molecules, such as neurotransmitters and many hormones, act through G protein linked receptors. This kind of receptor spans the cell membrane, and as you might guess, it works through a protein called a G protein. Click on the correct signal molecule to activate the G protein linked receptor shown here.
So here are your 3 signal molecules. Which one do you think it is?
I mean, the middle one.
Middle one?
Yeah.
Alright, let's click on that here.
The one that fits with it.
When the signal molecule binds to the receptor becomes activated. It is now able to activate a specific G protein by causing GTP to displace GDP on the G protein. The activated G protein then binds to another protein, usually an enzyme, and alters its activity. Then the G protein hydrolyzes its GTP and reverts to its inactive form, ready to respond to another signal. Click on another receptor type.
All right, so how did this enzyme become activated? What happened to it? Yeah, this G protein that was activated that has a GTP attaches to it. And what did happen to the enzyme when it attached to it? It changed shape. And so, therefore, this activated enzyme can catalyze a reaction now that wouldn't be able to happen unless this enzyme had become activated. And this enzyme doesn't become activated unless you have the signal molecule. So what you need to understand here, I want you to see the G protein moving through here. And so it moves from so the signal molecule binds and it has GDP on it, which means it's inactive. It only becomes active when the signal molecule binds and GTP replaces the GDP, and that's what activates the enzyme. So that's the G protein linked receptor system. Now I'm going to go through some examples here in just a minute. Let me do it smaller here so that I want to show you the tyrosine one.
Growth factors signal cells to grow and divide by acting through receptor tyrosine kinases. Click on the correct signal molecule to activate this receptor tyrosine kinase.
All right, so what signal molecule do you think this one? Circle, right?
Binding of signal molecules causes 2 polypeptides to join, activating parts of each that act as tyrosine kinase enzymes, which then phosphorylate tyrosines in the tail of the other polypeptide. The receptor protein is now recognized by specific relay proteins inside the cell. One tyrosine kinase receptor may activate several relay proteins at once, triggering several different effects within the cell. Click on another receptor type.
So I want to point out here that when these guys bind, it changes the shape in terms of these 2 polypeptides coming together. And once they're phosphorylated, notice it says that you have these 2 relay proteins, they're different shapes. That means that they are going to activate different proteins. So these guys will actually activate different phosphorylation cascades and lead to 2 different cellular responses. So one signal molecule in this case can lead to multiple cellular responses because they have 6 different tyrosine kinases on them. All right, 6 different enzymes versus the G protein linked receptor system, where the molecule binds to it, it activates one enzyme, which then triggers one phosphorylation cascade in one response. And so that's a difference there. And then the last one I wanted to show you is, oops, the wrong way, is this one here.
Some membrane receptors are ligand-gated ion channels. They are protein pores in the plasma membrane that allow or block the passage of certain ions through the membrane. For example, this occurs when one neuron signals another via a neurotransmitter. Click on the correct signal molecule to activate this ion channel receptor.
This one is
The signal molecule attaches to a site on the ion channel protein. This changes the shape of the protein, opening a channel through the membrane. Ions flow through the channel, and the change in ion concentration triggers a cellular response. Click on another receptor type.
All right. Last one is the intracellular receptor, but I'm going to hold off on that until later on in the notes. All right, so I'm going to go over some examples with that, but one other thing I wanted to point out with the website is that like it has the various different activities, things like that, similar to this, like that we just went over. But on the bottom, it also has, it says art for students, and it says download labeled and unlabeled images. So an example of one way to study is maybe printing out some unlabeled images with talking about different concepts, and see if after you study it, can you look at the image, can you describe what's going on, like literally write on it, write what's going on, because if you can't do that, then you don't really understand it that well, all right? So, because I've talked to quite a few people that, you know, like different things that they think that they knew because they read through their notes, but then when they try to explain it, like I asked them to explain it to me, they stumble up on it, like people that come in for help and stuff like that. And so, so that's a way to kind of test yourself, and you can write it down, check back in your notes and check back in the book to see if you got it correct, and then add things to it and so on. And so then that can be a part of your kind of testing yourself and your part of your studying as well. All right, so I just wanted to point that out. All right, so let's go back to the notes here. So let's go and look at some examples of this. So an example of a second messenger is called cyclic AMP. Cyclic AMP is CAMP. It's one of the most widely used second messengers. And there's an enzyme called adenylyl cyclase. This is the enzyme that converts ATP to this cyclic AMP. Cyclic AMP is a little bit different than just regular AMP. What's the relationship between ATP and AMP? What's the relationship, Nathan?
ATP has three phosphates and AMP only one.
That's right. So to convert ATP to AMP, you have to take off 2 phosphates. And so this enzyme, adenylyl cyclase, does that. So let's look at this picture here. This shows you this relationship here. So here is that adenylyl cyclase that we just wrote about. So this is your enzyme. And this enzyme catalyzes the reaction. The reaction that catalyzes is converting ATP to cyclic AMP. So this is just showing you the picture. Here's ATP, the structural formula there, and converting to cyclic AMP. And how it does that is it takes off 2 phosphates. And so these 2 phosphates here, when they're bonded together, they call it pyrophosphate. So that takes off the 2 phosphates, and we get AMP with just 1 phosphate. And then this just shows you that the structural difference between cyclic AMP and just regular AMP, they both have 1 phosphate. The difference is this bond right here. All right, so the bond angles here, the angle is changed, and we have an additional bond there. And so, so that's the difference there with the 2 kinds. There's an enzyme that can convert this to regular AMP, but what we're really concerned about is this. All right, so ATP gets converted to cyclic AMP. All right, and this by this enzyme. So now let's look at this in an example. So many signal molecules trigger the formation of this CAMP or cyclic AMP. Other components of CAMP pathways are G proteins receptors, and protein kinases. So that's what we just talked about with the activity we looked at with the video. Cyclic AMP usually activates protein kinase A, which phosphorylates various other proteins. So protein kinase A, when it says phosphorylates various other proteins, they're triggering a phosphorylation cascade that we looked at the beginning of the hour here today, at the end of the hour yesterday. So cyclic AMP activates it. There's other regulation that can inhibit that same enzyme. So we're going to talk about activating that enzyme, but we also can inhibit that enzyme so it doesn't work as well. All right, so let's look at this picture here. So this picture, what this is showing you here, if we don't look at anything down here, this is the G protein linked receptor system that we just looked at in that activity. So here is your what we call your first messenger. That's your extracellular signal. That means it's outside the cell. An example of that is epinephrine. Epinephrine is a type of hormone. And so it binds to the G protein linked receptor. That triggers, remember that this becomes active, which triggers, they're kind of skipping steps here, assuming that you remember what's going on with the G protein linked receptor system, that the G protein originally is GDP attached to it, comes over here, and GDP leaves, and GTP attaches it, and then it comes over here, and activates this enzyme. So this is an activated enzyme, and it's adenylyl cyclase. It gives you the name. So this is your activated enzyme. What happened to make it activated? So the G protein with the GTP came over, and what happened to the enzyme? It changes shape. So it changed shape. Now it has the right active site, the right shape of the active site to catalyze a reaction. So this enzyme is ready to go. So what reaction does this catalyze? Going back to this picture here, adenylyl cyclase, the enzyme catalyzes the conversion of ATP to cyclic AMP. So ATP is the substrate, cyclic AMP is what you get at the end. So that's why it says here, here's your enzyme, here's your reaction. ATP is going to come over here and get to the active site, and then the enzyme is going to help convert it to cyclic AMP. So I'm going to put here the ATP is the substrate, and this binds to the active site of that enzyme, and then is converted to cyclic AMP. So that's what that arrow is representing. I guess I can write binds to active site and is converted to cyclic AMP. So then the cyclic AMP, this is called your second messenger. And the second messenger would not be in the cell if the first messenger didn't bind here. Because then, all right, so then what does this do? So this now activates protein kinase A. So this, the second messenger, activates PKA, protein kinase A. So now this is in the active form, and what does that trigger to do? It's going to activate another protein, which is going to activate another protein, and so on. And so these arrows represent, from the previous picture, that phosphorylation cascade. Until eventually you get, at the end, the last molecule that is activated is a protein that's going to give you your cellular response. And so this is your cellular response at the end. So what I'd like you to do is, I'm going to have you look at a real life example of this. And so you should have a textbook on your desk left there from last hour. If you turn to page 211. 211. All right, 211. If you look at the page 211, on the left-hand column, the second full paragraph, it says, now that we know about the role of CAMP. See that? Second full paragraph on the left column of page 211. I'm just going to have you read that paragraph for a minute.
It's probably an antibiotic. So it's not like. I think a lot of people die in those countries because they don't have access to that, but I think having someone that sees it.
So this paragraph is describing what happens when people get a disease called cholera. Cholera is caused by a bacteria called Vibrio cholerae, hence the name cholera. And what happens is that bacteria goes into the human body and produces a toxin, and this toxin has adverse effects that actually affect cell signaling and causes this very serious disease that can lead to death. So what cholera does, though, the bacteria that causes cholera forms what's called a biofilm on the surface of your small intestine, of your digestive system. And did we talk about biofilms in here? No, I don't believe so. Okay. Let me show you a picture real quick of biofilms and explain what those are. Go back to what a biofilm is bacteria can adhere to surfaces of things. And so this picture here, let me erase all the notes on here, is showing you that up here in A, where it says free living prokaryotes, that's your bacteria. And what it does is it can bind to the surface, and when it binds to a surface, it starts secreting what they call a polysaccharide matrix. It's a chemical that comes out, and it's kind of sticky, and over time hardens. And so what happens is this bacteria is in this matrix here and begins to divide and so on. And this matrix is helpful for the bacteria because it protects the bacteria from the environment. So for instance, when we have bacteria that form this biofilm, this bacteria is in this matrix. So you have this bacteria secreting this matrix, they're dividing, making more bacteria, so that's what this is illustrating here, and they're just all secreting more matrix and so on. Eventually this matrix hardens, and even our medicines can't penetrate it, and so we can't kill the bacteria, which is beneficial for the bacteria. And so what happens is, this kind of relates to what we talked about with the TED Talk video with bacteria, is once there's a certain density, these molecules secrete these signal molecules, or these bacteria secrete these signal molecules, and once they're in enough density, then they secrete another molecule, and that's released out of the matrix and goes and actually causes other bacteria, other types of bacteria, which are the squiggly lines, to come and be part of this matrix. And so then we have these little squiggly line bacteria and the original bacteria and so on. And you have this whole colony of different types of bacteria all now secreting this matrix. And then this matrix hardens and they can live there and we can't get to them, basically. All right, so this is what happens. This is actually what plaque is on your teeth. You know, the stuff that the dentist scrapes off. That's a biofilm that has been on your surface of your teeth. So that's why it's important to brush often, because what you're doing is you're getting the bacteria in the matrix before the matrix hardens. All right, so if you let it sit and you don't brush it off and get that off, then it'll harden, and then you can't. There's nothing you can do besides scrape it off. So nothing's going to cause that to leave. And so I can do it on any surfaces, so that's why also it can do it. That's why you clean contact lenses. They can form biofilms on there. People who have like joint replacement surgery and things like that, they have something artificial in them, like a metal joint or something like that. The biofilms can form on that. I had a student last year that happened to her dad in a hip replacement surgery, and so it was a big problem. He survived it and everything, it was fine, but he had an infection with that. All right, so that's what biofilms are. So this is happening in the inside of your small intestine with this bacteria. And this bacteria, cholera is not very prevalent in this country. That's because we have good sanitation systems, because this bacteria is found in fecal matter. And so if people who get cholera are usually drinking water that has not been sanitized, and so therefore there may be waste with the water that they're drinking. So a lot of third world countries that use the same water system to wash their clothes and bathe and put their solid waste in as well, and that's their drinking water too, will get this disease. So it's very prevalent in countries like that. So that's the kind of background about it. And so what I'd like you to do is on the back of the sheet that you picked up here where it says HIV, it talks about HIV on the front. On the back side is what I want you to look at right now. The back side gives you this picture that we just looked at about the G protein link system and cyclic AMP and so on. And so if you read the directions at the top, I want you to use the picture to describe how this bacteria, Vibrio cholerae, affects us. And so it affects us by affecting the cell signaling system. So what cell would that be part of? Where at in our body? And what I want you to do is use that diagram. You can to explain how the Vibrio cholerae toxin is affecting that diagram. Okay, so that's what I want you to do right now. So I want you to put in words what that is doing.
How would it work? It does not cause you to come on to deactivate these things. Okay. I just said like you should stay there, even though it shouldn't.
Don't read it.
Why are you targeting this at me?
I'll let you know.
What the heck, guys?
So it's an enzyme. So the bacteria, and the line is it's an enzyme called color toxin.
They said you could modify it.
Vibrio color. Yes. Wait. Okay, it's the G code itself, the G code itself, isn't unable to dehydrolyze or unable to stabilize the
Enzyme substrate complex. It's not able to
Mrs. Walker, could you move that over?
two options. It is in the
Secretion of water. Like,
and other enzymes like digestive enzymes. And so
yeah, it's like allowing the water to salt.
I've watched it.
Secretion.
So this toxin that the bacteria releases, somebody want to explain how it affects the system?
Doesn't it always just make the G protein active, so like it keeps the GDP there, or GTP, and then the system really shuts off when needed because it just keeps going forever.
That's exactly right. So in this case, so what he's saying is, remember this comes over here and binds, so I have the GTP, and this activates this enzyme, and so it keeps this in the active state. So therefore, this enzyme stays active, which then, as Nathan said, then is always going to convert ATP into cyclic AMP, and therefore you're always going to get your cellular response. And so, in this case here, what is the cellular response? Maria?
The secretion of water and like and salts for digestion.
Yeah, secretion of water and salts. So this is gonna continue to happen. So what does that mean, secretion of water and salts? So let me explain here. So you have your digestive system. I'm just gonna do a very brief, here's your mouth. Food goes down through your esophagus. And then it connects to your stomach. So this is your stomach. Your stomach connects to your small intestine, all right, which is long and windy. And then eventually, so this is your small intestine, and then eventually you get to your large intestine, and anything that is not absorbed into your body leaves as solid waste. So this is kind of what we're looking at. And this is in the membrane of what kind of cells? The small intestine. And so when we look at this here, when we're looking at a section of that, this brown here is a bunch of cells, intestinal cells, and this is going on within those intestinal cells. So what's going on is that this system is always on in these cells. So when we say that, then we're always going to get secretion of salts and water. That's what actually happens here. So these cells are secreting salts into your small intestine. And what that does is it create what kind of environment? What does it do to water concentration?
It makes it so hypertonic.
Yeah, salts would decrease the water concentration, which would make it so that now these cells are bathed in a hypertonic solution. So what's going to happen to the cells? Water is going to go out as well. So you get more water going out. And so you have this continually happening in the cell because this enzyme is always on because of the active G protein. And so now these cells lose salts and water, and it goes through the rest of your digestive system and leaves a solid waste, which then makes a big symptom of the people that have cholera, diarrhea. All right, and so the solid waste is very watery. They're losing a lot of water. They're also losing salts. Salts, we're going to see later on in the course, are very important for a lot of different reasons. Certain salts and ions are useful for your neurons to work in your nervous system. It's also useful in keeping water balance, and so losing a bunch of salt and water. And so what happens is people can eventually die of dehydration and the loss of these salts through this process. And that all has to do with this toxin that affects this G protein linked receptor system. All right, so that's just an application of that. I also wanted to just point out that is something that this activity is something that you could do on your own. So like notice that we read a paragraph. Science reading is not like a novel, all right? So you can't, oftentimes when some people can do this, but not most of us, would read that paragraph. Some people then look at that diagram and maybe we're able to spit off the top of their head and explain what happened off the top of their head. But my best guess is that most of you had to look back at the paragraph to relook at it and so on. So that's just an illustration about how you can read something and say, okay, I get it, it makes sense, but not really, all right, because you can't explain it on your own. So that's something that can be useful when you're looking at your notes or reading the book is a technique. And so tying back to, you can print out diagrams yourself and do that kind of thing to help as part of your study process as well. All right. So that's one example of a second messenger cyclic AMP. I'm going to give you a second example of cyclic AMP. The second example is with calcium ions. Calcium ions act as a second messenger in many pathways. It's an important, cells can regulate its concentration. So if we look here at a cell, this is this picture. The purpose of this picture is to show you where the varying concentrations of calcium are in the cell. So in my picture, the dark blue is the high calcium ion concentration. Yours is like the gray. And then the light blue, which is the cytoplasm, appears white in yours. So that's the white in yours, which is the cytoplasm. Because it's not really color-coded on yours. So. And so when we look at this, outside the cell, there's high calcium ion concentration. Inside the ER, and inside the mitochondria, and then the cytoplasm, there's a low concentration of calcium. So let me ask you this. If calcium can move through the lipid bilayer, where will it want to move to? Into the cytoplasm or out of the cytoplasm? Calcium move into the cytoplasm, and it doesn't matter where. Will it move into it from the extracellular fluid outside the cell, or into it from the ER or the mitochondria, or is it going to move out of the cytoplasm? It's going to move into, and why do we know that? Because it's going to move from high to low concentration. So there's high concentrations inside these two organelles as well as outside the cell. So if it can move, it's going to move into the cytoplasm. Calcium, it's an ion. Can ions generally move through the lipid bilayer? No, they cannot. Hydrophobic things can move through the lipid bilayer, but not charged things, and ions have a charge on them. So they can move through the lipid bilayer, so that means ions have to have a what to move through the lipid bilayer? A transport protein. And the thing is that there are not transport proteins that allow calcium to openly diffuse. And so therefore, calcium stays where it's at in the either in the organelles or in the cytoplasm. But what can happen is that there are, and I'll talk a minute about these pumps. Don't worry about this right now here. But what can happen is that there are gated ion channels that can open and close and allow calcium ions to diffuse. So a signal relayed by a signal transduction pathway can trigger an increase in calcium in the cytosol. And this pathway leads to the release of calcium, and it involves two molecules. We're just going to call it IP3 and DAG as second messengers. So this is what we have here. So let's look at this step by step here. So this part right here is our G protein linked receptor system. All right, so it's the same as before. Is the receptor is the G protein that becomes activated, which activates an enzyme. So this enzyme is just different than the last example we looked at. The last example, the enzyme was adenylyl cyclase. So this is now a different enzyme, but this is the enzyme that becomes activated. And it becomes activated from the activated G protein, which became activated because of the signal molecule. All right, so the signal molecule triggers this. So what does this enzyme do? It triggers the this molecule called PIP2. That's not important here. It triggers it to kind of break down into two separate molecules, the DAG and this IP3. The IP3 is the second messenger. So what this is going to do, what does that mean? It's going to cause a change to happen inside the cell that's going to eventually lead to a cellular response. It's called the second messenger because it's the second molecule that's going to trigger a change after the first messenger, which was the signal molecule. So looking at this picture now, this IP3 is only in the cell because the signal molecule bound to it, to the receptor, and now we have this IP3 in the cell. According to this picture, what does IP3 do you think? Max?
The other thing that the calcium.
That's right. It opens the gate to allow calcium ions to move through the membrane from the ER into the cytoplasm. So notice here it's an IP3 gated calcium channel. So it's gated, it opens and closes, and so at first it's closed, it only opens in response to IP3 binding to it. And so now it's open and allows calcium to go through. So this IP3 gated calcium channel opens when IP3 binds to it. So now this channel is open, and now calcium ions go into the cytoplasm. Is this passive or active transport? It is passive. How do I know it's passive?
Because it's moving down its concentration.
Moving down its concentration gradient, it's going from high to low. So we have a high concentration of calcium ions here, a low concentration of calcium ions here. So therefore, this arrow here represents diffusion, high to low concentration, which is passive transport. So now this calcium diffuses out. And now what does this calcium do? This calcium acts as a second messenger. One would think that it might be called the third messenger, all right, but it's not. They call anything after that first signal molecule a second messenger. So what happens is this calcium now is floating around in the cytoplasm. What does that do? It activates proteins that will then activate proteins that lead to the cellular response. So these various proteins activated, this right here, this will trigger phosphorylation cascades. So the protein one protein will be activated by the calcium, which will activate another protein, which activates another protein, which activates another one, until eventually we activate the protein that's going to give you your cellular response. Okay? All right. And so that's what that means there. So now, what happens is that as calcium diffuses out, do you think the IP3 stays on here forever? No. So then the IP3 will detach, the gate will shut. But over time, do you see that the more this happens, so then let's say another signal molecule comes and so on, and more calcium, do you see how you'll eventually get higher and higher calcium concentrations in there? So what happens, this is the purpose of going back to this picture here. Notice that the places like the ER that we just looked at, they also, in addition to the gated ion channels, so they have the gated ion channels here that will open and close in response to IP3, and then the calcium can diffuse out. So what happens is now they also have a calcium pump, which pumps calcium back into the ER, so that you always have a high concentration in there. So then that way, the next time the signal happens and you get the IP3 here, it'll still, calcium will diffuse out. Does that make sense? All right. And so it makes it so if this is active transport, remember pump means active transport, and it's showing that by using 18. This is where we'll stop for the day.